Hi everyone, it's so cool that you're here. It feels like it's been a very long time since the last in-person conference, so this is really nice. It's a bit new again. If it wasn't obvious from the awkward hand waving from the corner, I'm Jan and this is Christian.
Hi.
And yes, we are both data science / data engineers at Quantco. You might be a bit confused because the title of this presentation has changed slightly. However, semantically, it has stayed the same. We're going to talk about decoupling model training from inference using onnx. Maybe with regards to a bit of a glossary here. What do we mean with inference? Inference is a word that we use quite heavily, maybe excessively. We basically mean making predictions. So if we also try to stick to the word prediction. If you catch us here, the word inference, that's what we mean. Okay, so why is decoupling model training from inference so important, or why do we think it's so important? Well, I probably got a point to there, yes. Well, I recently looked up from some survey that 55% of companies who have started with machine learning have failed to put their models into production. And this number is from 2020. I doubt this has changed much since then. And I mean, this is a pretty big number, right? 55%, and even though there might be many benefits to having machine learning for maybe exploratory reasons or other purposes, I still argue that being able to maybe enhance a business process or automate something by putting a model into production is where the majority of the value lies. So if you fail at doing that, then maybe you're missing out on the majority of the cool stuff you could do. And well, considering that so many companies fail at it, deploying models seems to be more complicated than it might look at first glance. So this is basically what we want to convey. Today, we want to show you why it is so difficult to put machine learning models into production and how onnx, as a universal file format for machine learning models, can help you overcome this challenge. And at the end, we want to convey a bit this idea of thinking in onnx and how you can convert your own models into this specification. And with that being said, I would pass it over to my colleague Christian, who could maybe tell us why this is so darn difficult.
Yes, thank you very much, and also hello, and thank you for coming from my side. As Jan just mentioned, it seems that sometimes the deployment just seems to be harder than initially thought. And in the following, we just want to walk you through the process how a machine learning project probably quite often actually starts out and then sort of develops and then sort of well, collides with the requirements of deployment.
You got a point to here.
Yeah. Okay, so your common projects, given that you're at a Python conference, I would be not surprised to learn that some of these projects here to the left-hand side are somewhat familiar to you. This is probably the tool set you would be using to start with your machine learning projects, to do the data exploration, then to build your first model, to, yeah, just essentially build your model. Now, why would you do that? What do we appreciate about these models? They really give this fast iteration, debugging, data exploration. We can then sort of visualize our current results and then go back, change everything. Okay, so we would do that using these tools, maybe for a few months. Then we finally have a nice complex model that performs nicely, gives us good results as we expect. And then, well, I suppose it's time to move our model that we just built using these tools into production. I'm just going to use the button. Well, now sort of it's the time to look up, well, how would we do that? We go to the scikit-learn documentation. We look at chapter 9, model persistence, and we find, okay, well, there are not a lot of options. We take the very first option that is presented to us in the official scikit-learn documentation, and it just says, well, pickle your model, lack of options, I suppose. So that's exactly what we're going to do. We pickle it, we ship it. Done. Deployment is actually easy. Thanks for coming. Yeah. Well, let's see how this devolves in in the deployment. Yes. And the way we are going to do this now, I'm going to be the data scientist to some extent, who just built the model. and Jan is going to be the data engineer who actually then sort of tries to put it into production with a web service, and we're just going to do a bit of play back and forth. So I just pickled the model, and now I hand it over to Jan.
Yes, exactly. So I received the model. I don't know how sophisticated your model exchange process is. It might be something like passing it over Slack, or I don't know. You'll find a way to get the model to me. And so I get this file. I'm like, okay, what's this pickle? And basically what I'm trying to do at first is to build a REST API around it, maybe use Fast API, use Flask, make it available to our external microservices. And so I basically unpickle the thing, and that's the first thing I get. Module not found, no module named sklearn. I'm like, what does that mean? What is going on, right? And this is the very first thing that some of you might be aware of, but maybe not all of you. Pickles are not fully self-contained. In fact, to unpickle something, you basically need the exact same packages that you used during training to reuse your pickled Python object. And there's a myriad of terrible, terrible consequences with that. And we're not going into depth with security concerns and all these funny things you can do when unpickling something. There's funny talks out there already about this topic. But basically it means, now I'm saying, well, Christian, I can't unpickle this. What am I supposed to do now?
Well, probably you're going to look up the documentation on pickle, as you just said. You will learn. You have to just reproduce essentially the environment, or at least all the dependencies that are mentioned in the pickle in your deployment. So in this case, we certainly probably want to have pandas and scikit-learn as our dependencies. Depending, maybe we use some custom classes with some plotting functionality. Maybe we need even more matplotlib, etc. So what we probably would do is we just take our training environment and completely put it into our production environment with all the dependencies. And there you go, you can load your pickle.
Yeah.
Again, how hard can it be?
That's when I start rolling my eyes and I start installing all these dependencies that I suddenly need for unloading this pickle. And yeah, admittedly it works. I need to be very careful to have the very same versions installed and all these things, but yeah, I can make it work. And I put it into the REST API, I put it in production, and I let it run. I do my benchmarks to make sure it's performant, and then next roadblock. The model is too slow. Because maybe I have a specific use case where I send single row requests to my model rather than batches, and I want them to be very snappy and very responsive. And suddenly I have this major sklearn pipeline which takes hundreds of milliseconds to make a single response, and I'm like, I can't put this into production in a microservice. It's too slow. And I start looking into Christian's code, and I see a bunch of for loops, and I'm like, what are you doing there? You got to make this more performant, man. And so I basically say, you got to do something about this, and I pass it back to him.
Well, and I do, of course, what everybody in this situation would do. I replace the for loops. I essentially go back to the model. I change the model. I sprinkle some NumPy magic on top of it, where it benefits, maybe even some number. And yeah, there you go. It got faster. Your latency went down.
Yeah.
Oh no.
Nice. That was possibly the wrong button.
Yeah.
There we go.
Here you go. So again, we're good. We can put it into production. Finally.
Exactly. I think at this point we're 2 weeks in at least. But finally we got it to work, and it's been running for a while quite successfully. But then suddenly, a couple of weeks or months later, I get this email from business, and they have this fantastic idea of, why don't we use the model directly from Java? And I'm like, what? How? How are we supposed to do this? This is a Python object. What am I supposed to do now? And I also just look at Christian, do you have any idea what I should do now?
Well, in this case, I suppose we are somewhat out of ideas.
Yeah. Should we just re-implement it, or what are we supposed to do?
Exactly. Of course, we could just say, well, I guess we have to re-implement everything, and then a framework that sort of would be more amendable to be used directly from Java instead of essentially interfacing with Python. Or we take a step back and we look a little, why did this deployment actually turn out to be so difficult? What if we could just use the tools we really like for our data exploration, for our training of the model, and then we have this universal file format where we essentially export our model to, and then from this universal file format, we are then free to choose whatever runtime we want to use in production. It doesn't need to be we can use scikit-learn here on the left-hand side, and then we just use this universal file that we exported to, and we load it into a runtime with nice Java bindings and good performance. Now, again, or what would that give us to sort of like really put it into like explicit words? What we want to do is we want to really decouple our training from our prediction time. So we want to use the tools for training, we want to use, then export it to something universal, and then be completely free in our tools we want to use for deployment. Now, again, if this were a pie in the sky, we would probably be not holding this talk right now. So fortunately, there is already quite an ecosystem. I keep hitting the wrong button, I'm sorry. There is already an ecosystem. There is this universal file format. It is called ONNX. We go more into detail there later. And then on the prediction side, there are these interpreters or runtimes that take this universal file format and essentially interpret your model. So, for example, the reference one is called ONNX runtime. It's here on the right-hand side on the very top. It's a C++ library with nice bindings in all sorts of languages. But there are also other runtimes that are more geared towards embedded devices, for example, a Pi0. Or you could even do crazy stuff like take your model and completely compile it down into machine code here with the last project on the right-hand side. And then, of course, not explicitly mentioned here on the slide, but if you want to go from your trained model to the ONNX format, so the left-hand side of the hourglass, you also need converters that take your scikit-learn model and then sort of put it into the file format. We're going to talk about that later, but also those already exist. Now, ONNX. What is it? How does it work? Let's go to their homepage and take a look. And we are greeted by a name that, frankly, might not sound so encouraging depending on what kind of models you are building, because ONNX is the abbreviation for Open Neural Network Exchange. And before you sort of then close your tab in disappointment because you're like, oh no, I'm actually not using deep neural networks, I'm using linear regressions or tree models or whatever, rest assured, this is just not the best name for the project because this is really generic for all kinds of machine learning. So it is not limited to neural networks. Now what it is, to like re-emphasize, it's the standardized way to describe your entire model, including your feature engineering, and to store it into a binary format. That is, in essence, what it really is. And around this specification, that is now a few years old, actually, we have a growing ecosystem of converters from scikit-learn to this file format and runtimes that essentially then interpret your model with whatever properties are best for your deployment. And also nice benefits are it's with a liberal license, so you will not have a problem actually using it in your deployment. And it really does have good corporate backing in this case, like the ONNX specification and also the ONNX runtime that I mentioned on the previous slide are actually both developed by Microsoft. So it's not like some hobby project or something. Okay, so ONNX, this is all very theoretical. Let's look a little closer. How does ONNX achieve all these promises? Okay, so this is really one of the most important points to take away from this talk. ONNX, you need to be able to describe your model, or you need to think about your model as a computational graph, namely as a directed acyclic graph, so without loops. If you can sort of put the logic of your machine learning model into this sort of computational flow, where you put the input in at the top, and then it goes to an operator, like in this example, for example, the add operator, and then the result from that goes to the next operator, in this case a linear regressor, and then you get the output back. If you can put your model into this kind of format, then it works for ONNX, and this is exactly how ONNX describes your model. Okay, so the nodes, as I just said, actually are operators. There's a whole set. I'm going to mention that in a moment. And the edges, they are actually the data flowing through your graph. Important side note, ONNX is strongly typed, so all the edges actually have type information, like be it float, integer, strings, and actually also shape, but that's not so important for our case here. Okay, so this is all nice and well. What does ONNX specifically say? So ONNX defines as a set of operators, so you can't just willy-nilly make your own operator named XYZ and think it works. No, of course, it has to be like in the set of specified operators. At the time of making this talk, there are actually 175 operators out there. So it's not only like easy stuff like add, it's really also like more involved ones like linear regressor or true ensemble regressors, etc. So ONNX defines these operators, and then also like this the stuff you need around it to actually then sort of put all the operators into a graph and to store the data associated with each operator. So add might not have data associated with it, but the linear regressor, of course, has been trained on your data. So you need to store those coefficients somewhere, and ONNX defines that so that everything is self-sufficient, contrary to the pickle before. The ONNX file you get at the end is really completely self-contained. No other dependencies needed for reading it in. Okay, so let's take a closer look at what, for example, the specification for one of these operators might look like. Just one example of these 175 operators that is not too complicated and not too trivial. So I chose the binarizer. You might be familiar. It's essentially an operation where you get an input value. If it's above a certain threshold, you set it to 1, or the output is 1. If it's below a threshold, the output is 0. So obviously, for this operator, you need to store the threshold. So the ONNX standard specifies, okay, for the operator binarizer, you need to store a floating point value with a threshold where you make the split. And then this operator gets exactly one input array of type T and produces exactly one output array of the same type as the input. And in general, this operator is then sort of implemented or should be implemented by the runtime for the following types at the bottom, namely what you would expect, I suppose, floating points and integers. Okay, and then for all 175 operators, there are like these kind of definitions of what it expects as input, output, and what attributes can be stored with it. Okay, all nice and well, very theoretical. What you know at this point is there is some format that claims to be able to store your machine learning model in a generic format, and that can be read by other stuff. Well, okay, again, theoretical. Now Jan is gonna tell you a little more, put a little meat to the bone and tell you more of how you can actually convert your existing model into this ONNX format.
Yes, I will try to. So this is probably a point we'll keep on repeating over and over and over again. But in order to convert whatever you have to ONNX, it needs to be representable as a directed acyclic graph that only uses operations specified in the ONNX framework. And there we go. In fact, and that's also something we want to stress because many people don't really realize that it's not really limited to only converting your estimator, which is possibly only the very last step in your pipeline. You can convert your entire pipeline, and there's nothing that limits you from doing that. In fact, I would go as far as saying you can convert almost arbitrary code to ONNX, assuming you can represent it as a directed acyclic graph. It doesn't have to do anything with machine learning, if you think about it. It could be any algorithm. It could be anything that follows a certain AST. The only thing is that shouldn't have any loops, etc. Should be representable as a directed acyclic graph. And coincidentally, well, machine learning pipelines, in essence, are directed acyclic graphs. If we think about this toy example of a pipeline with 4 steps, you can see, well, they have arrows. That's always a good point for them being directed. There's no arrows going back to the beginning, so that means they're not acyclic. And this is technically a very simple example of a directed acyclic graph. However, to be compatible with ONNX, we also need to be able to represent each and every step in this pipeline as a directed acyclic graph. So basically, what is now a node in our graph on the sort of abstract scikit-learn level will turn into a graph itself in the ONNX level. And what I mean with that is, for example, if we look at the simple imputer on the left-hand side, and we assume it has a very, very simple implementation where it's just a bunch of NumPy operations. We first create a mask, so we find the missing values, we store that information, and then we replace the missing values with a defined impute value, and for all other values, we just pass on the original values. So it's a very simple NumPy operation, which can very easily be defined as a graph of ONNX operators, which would look basically like this. So basically, on the scikit-learn level, we would have a simple imputer. When we convert it, it's going to be a graph of an input, an impute value, an is-none operation, a where operation, and a defined output. And to give you one more example to really make that sink in, we could do the same for the regressor. A regressor is not a black box, right? We know how it works. It's essentially a matrix multiplication of coefficients and inputs, and an addition of the intercept. And essentially, usually all that you really need to look at is how is the transform or the predict method of the corresponding class implemented, because that shows you what is the actual underlying algebra, the mathematical formulation of this step that you need to express. So I think this gives you a good idea of basically how by replacing every node in this scikit-learn graph by a graph itself, we convert scikit-learn into an ONNX format. Yes. And so now the question is this lots of work? And well, it depends, as always. If you only choose to stick with established machine learning frameworks, scikit-learn, PyTorch, TensorFlow, LightGBM, XGBoost, chances are somebody has written these converters for you. Maybe that's also a strong point to emphasize, as opposed to something like Numba, where they basically inspect the source code and compile things on the fly. There's no such thing for ONNX. You, at some point, have to manually say, well, the representation of the inference logic or the prediction logic of this class maps to this graph. And somebody has to do the hard work. And again, as this is very well maintained by lots of bigger tech corporates, many of these conversion functions, this conversion logic, it already exists, and you can just use it and be done with it. If you happen to have custom estimators, custom transformers at your company, you will need to write your own converters. And this can be painful, or it can be relatively easy. The learning curve is a bit steep, but you can make it work. It is technically feasible, assuming it fits into a DAG. That is, I think, also a very, very important takeaway here. And these are all the libraries that you will probably be able to use almost out of the box, because converters have already been written. Namely, there's things like onnxmltools or skl to onnx that can convert these libraries. I think it covers pretty much everything. All right, on to the live demo. What could possibly go wrong? Okay, I think the first thing we got to figure out is how to zoom in. I remember this was a bit of an issue at yesterday's lightning talks, but this was a lot easier than back then, if anybody was there. So, we're basically the thing that we did in this very amateur theatrical play earlier on stage, we're now doing in code, right? Right now we're in the training phase. It's the data scientists building their model. They're importing a bunch of stuff from scikit-learn. Just that you see, this is a fairly recent scikit-learn version. Just doing some config stuff that is not particularly relevant, making sure that my tests don't fail, so I'd rather set a random seed. And now here I'm producing some artificial test input and an artificial test output. So the input for our pipeline that you will see in a second is basically an array with floating point values between 5 and 10, some of them being non-value, so we have a couple of empty ones. And our target variable is also just a bunch of floating point numbers, essentially. And we can create a pipeline like this. I think you should mostly be aware of that, like how to create pipelines in scikit-learn. We can visualize it. This might look familiar. This might look very similar to what we just had on the slides. And I'm going to go ahead as a good data scientist. I'm going to fit this on the entire data set, as you're supposed to, which usually gives great training accuracy. Yeah, at this point, I'm pretty much done with my workflow, right? I've trained a model, I'm happy. And now I want to make this available to the data engineer. So I'm going ahead and using the existing conversion libraries. And as we said, in the case of scikit-learn to ONNX, It's quite simple. We import a simple function called convert sklearn. We also have to import a bunch of different data types. Why is that the case? Well, since ONNX is strongly typed, it needs the initial information of what you pass on to it, or what you provide to it, and then the subsequent types can be inferred from the operations, but the initial types need to be provided. Now, you can infer the types very easily. If you, for example, have a pandas data frame, you can write a very simple mapping of the pandas data types to the ONNX data types. This is what we do internally at Quantco, but for the sake of simplicity, we just basically hard code that the initial types for this ONNX graphs are going to be a float tensor type with 10 columns and arbitrarily many rows. And then we pass all this information on to the conversion function, and it goes through very quickly, and we suddenly have an ONNX model. And the ONNX model, it defines a bunch of metadata that we will not go into depth, but the most relevant part is what you see here as graph. You can see it defines a couple of nodes. Here we can see this is an operator of type imputer. It defines a couple of attributes, as we saw earlier, a couple of like different other nodes. A whole bunch of stuff is in here. And this is a fully self-contained mathematical extraction of the prediction logic of your pipeline that has no remaining touch points to the original scikit-learn model. So this is it, basically where the data science responsibility stops. All you now have to do is basically dump this into a file and again make this available to the data engineer. Everything that happens from this point onwards could technically happen in a completely different environment with different dependencies, on a different day, in a different year, by a different person, but for the sake of the simplicity, this happens on the same notebook. But again, we completely decouple things. So now, as a data engineer, I'm quite happy because the only actual library, the only actual dependency that I have is the ONNX runtime, and that is consistent regardless of what kind of model I have been serializing before. So no matter whether the model came from TensorFlow, PyTorch, or scikit-learn, my only dependency that I have here is the ONNX runtime. So I import this inference session class and I instantiate it by basically passing on a file path to a model file. And then again, the API is not fantastic, but it gets the job done. You can write a very simple abstraction around it. You basically run this session object. You say what kind of output from the graph, like every node has an ID, so that's the ID of the output that you want to get the data from. And then you provide the inputs as basically a mapping of the input ID to the data that it should be passed on to. Then you need to do a bit of reshaping because, again, API is not great, but I'm sure you could figure that out on your own. And then to prove that we're not lying and that the predictions are actually the same, up to 6 decimal places, drum roll, nice. So scikit-learn and ONNX produce the same predictions to us, satisfying accuracy or precision. If you're curious why the predictions are not exactly the same, we can maybe talk about this after the actual content of this presentation and just go a bit into like the nitty-gritties. But in the majority of use cases, being accurate to 6 decimal places should get you most of the way. Another thing that we complained about at the beginning was inference speed, so prediction speed. So we set up a very simple benchmark. The first thing that we're going to benchmark is the prediction time on the overall batch. And if I remember correctly, the input data had 1,000 rows. So with scikit-learn, let's see how long this is going to take. 500 microseconds per loop in average. And now let's check with ONNX. And again, here we're using the default ONNX runtime, which is written in C++ and provides Python bindings. And we're down to 30 microseconds, so that's quite nice. That's factor 10 on something that was already very simple and optimized to begin with, because we didn't use anything fancy in the original pipeline. It was just a linear regression and an imputer, essentially. And what was also very, very relevant for us, especially in the case where you put models into an online environment and you want to make predictions in real time, we personally really care about single row prediction speed. And I just want to confirm that we're basically getting similar results here. Again, first for the scikit-learn case. And you can see that in just a second, This still takes about 170 milliseconds, microseconds on a single row. And with Onnx, we will go down quite a bit to about 7 microseconds. So, and to tell you a bit like a little story from our production use case, we actually managed to go down like 100 times, like 2 orders of magnitude rather than just 1, because just the ingoing scikit-learn object was so much more complex than what we've just described. All right, then I would say this we have seen. On to the summary with Christian.
Thank you. All right, so the premise of the talk was to demonstrate to you that oftentimes we start off a project, we use the tools we like for the very good reasons. Because at the very beginning of our machine learning project, we want this fast iteration and visualization and everything that we get from the default Python tools. But then if we follow the standard practice, even in the scikit-learn documentation, we essentially really end up coupling our training environment to our deployment environment. And we really lose many, many options of what we could then finally do with our model in deployment. Now, if you use Onnx, you can decouple the two, you can continue using scikit-learn, then you export it to this universal file format, and then you use something like the Onnx runtime or some other runtime to essentially read in your Onnx graph and to interpret it with whatever performance characteristics you actually need for your real deployment. Then, of course, there's the universal law of no free lunch, which means somehow you need to get your scikit-learn or whatever model into this universal format. Now, as you've just seen in the live demo, whether that's like almost no work or can get pretty involved kind of depends on exactly the nature of your project. If you stick to the standard framework, you should be pretty fine. If it's a little more custom, always think in graphs. Can you map your model into this directed acyclic graph with like these Onnx nodes as like the common denominator? Then you should be fine. It might still be a little bit of work, but you should be fine. If your model does some really funky stuff, then it might not be a perfect fit, but to be evaluated then. And yeah, so in any case, we can really recommend looking into Onnx for like many, many reasons, not only performance, but also like archiving it, etc. So it is a technology we are actually very excited about. And well, if you find yourself to also be excited about work like this, maybe look into Quantco. And yeah, that's it from our side.
Thank you.
Thank you.
So we can move on to the Q&A session. If you haven't, you still have the opportunity to vote for your favorite questions. And we have plenty of time left to ask the really tough questions. Because there seem to be quite a few skeptics in the audience, let's say.
All right, bring it on.
That's why the most upvoted question currently is, why not just throw everything into a Docker container, solve the dependency hell, and it scales nicely?
Well, there was the premise at the very end, wasn't it? And it scales nicely. Well, let's take a step back. I think there are like several things. Like if you throw it into a Docker container and you want to use the same model, for example, in 2 years' time, but maybe in a slightly different environment, then, well, it doesn't work so much anymore. Then you would need to use your old Docker container and call into it from your new environment, and not so nice anymore. And also, the scaling part is not really a given. It might very well be that your scikit-learn is not going to perform good enough for your use case, or that something changes and suddenly you can't use your Python environment anymore. And then if you sort of stick with like essentially just pickle it, put it in a Docker, that essentially still couples. Like you have to use those tools that you use because they're like nice and interactive and fast to iterate for your training. You still have to use them in deployment, and that really is not necessarily what you want. So yeah, I'm not saying that it doesn't work with putting it into Docker, but there are many things that might sort of just not work out so well, or where it would just be nice to have more flexibility in how exactly you deploy it. Also in our example, of course, if you, for example, want to train your model and then use it on an Android application from Java, it's not going to work so well with a Docker container. Yeah. But it would still be nice to actually be able to use scikit-learn.
Maybe like 2 more things as an addition, but I totally agree with what Christian said. So one thing is that, for example, the decoupling is a really, really important part. And for example, this, albeit maybe rather exotic use case where suddenly you want to have this running natively inside of an Android application or of a Java desktop software, you don't solve these things through Docker. The only thing you can actually do with Docker is basically provide a REST API, so basically the happy path, the use case that maybe is most relevant to you as a company. But yeah, the other thing is that with Docker, since you add so many other layers around it, like the archive or the artifact that you produce, it's not really just your model, it's all these other things as well. And by serializing it to ONNX and then putting it, for example, on disk, you have this pure essence of just your mathematical formulation of your model that you can always load back in and see, oh yeah, this is somewhat human readable. I can totally see what's happening here. You don't have that with putting it into a Docker image.
Thank you very much. I'm going to sneak in one question I just saw. Are you going to share the notebook, or is this available somewhere?
We can share it. We can totally share it, but it's not available yet.
Okay. You figure this out then.
Yes, I don't know. I'm going to text you all on WhatsApp. I don't know.
Next question. What are the cons of ONNX, and when should you avoid using it? There have to be some downsides.
How much time do we have left?
About 8 minutes.
Okay, cool. You want to start?
Well, yeah, okay. Yes, again, no free lunch, and also it's not like the perfect solution for every use case, no doubt about it. Again, if you use sort of the established things, a lot of the converters already work, and you get a lot of the nice stuff from ONNX almost for free. Then, if it's sort of you created your own classes that maybe inherit from some scikit-learn operators and do some extra stuff, you would need to write your own converters. Might be a bit of work, but probably works. Where you should really reconsider if it's like the best fit is if you, for example, need a lot of recursion in your model, or if you would need to do some funky stuff depending, like you execute halfway through your model and then maybe you have to fetch some resources, do some I/O or whatever, depending on sort of some state in the middle of your prediction.
I would add maybe one more thing to that, because the thing with the conversion, writing your own converters, we have a pretty big internal library with like a whole bunch of custom estimators and transformers. And I think writing all the converters was like 4,500 lines of code. So that was quite involved and took us quite a lot of time to get it right. But now that it's working, it was an initial overhead, and everything else, like from now on, we sort of get for free. The second thing that I mean, it's not really an ONNX issue, but it has no native support for categoricals. So if you have a lot of like pandas conversions and you do like categorical encodings and stuff like that, you need to be very creative on how to represent that. It's possible, we made it work, but it wasn't fun. So I think these are the two biggest issues, especially the second you could just solve by encoding everything into an integer or something at the very beginning of your pipeline. But yeah, it's a bit tedious.
Actually, I have one more thing to add. Sorry for the back and forth. But also, you should really be aware that this is a fairly new technology, and the ecosystem is rather new. So if you, for example, convert your models, it might be that you get like a fairly cryptic error message. And then you might have to dig in or look up some issues and whatever. It is a new ecosystem. It's not that mature yet. I mean, it's developing. And I think it's very promising, and I'm very excited about it, obviously. But yeah, expectation management, it is young. There are some rough edges. So if you don't want to spend your time reading through a GitHub issue or a pull request or whatever,
or fix something yourself.
Yeah. Then you might very well encounter some rough edges.
Moving on to something completely different, GPU acceleration. The question is, how easy is deployment on GPU/parallelization on several GPUs afterwards?
You? Okay. So the reference runtime, ONNX runtime, actually has, as far as I know, I don't have first-hand experience with it, but I'm pretty sure it has actually, it has some GPU tooling around it. So again, I no first-hand experience, but the technology is technically there, and it's built on top of CUDA as far as I'm aware. So it should just work with the default runtime. You can give it some options when you actually set it up, whether it should be single-threaded, multi-threaded, GPU, etc. So technically there, I don't have first-hand experience.
And then again, the specification itself is not limited in that way, right? It's just you need a runtime, and anybody can write one. You probably don't want to write one yourself, but technically anybody can write a runtime.
Okay, next question, this time about encryption. Is it possible to encrypt ONNX models for protecting trained models against unintended use? Example, reverse engineering to infer the trained model parameters.
Actually, well, half of the question, I'm very excited that someone did ask it, because, so taking a step back, if you, for example, were to use proprietary tools in your training, those are, of course, because the dependencies are not necessary for deployment, you can essentially keep them really separated. So when intellectual property is a concern in this regard, ONNX can also solve your issue. Can it be reverse engineered? Yes and no. So in practice, if you have a fairly complex model, you can read the coefficients out of the model, and there is even like nice visualization tooling that makes it pretty easy to find the coefficients in your model. But in our production model, I think we have like 20,000 nodes, and there is no, it doesn't preserve like, oh, this used to be this operator and this used to be that pipeline. So to some extent, it's security by obfuscation, I suppose, to some extent. But yeah, at the end, if you actually ship the ONNX file, it is fairly easy to get the weights. Now, there are projects, I did show it here on, we did show it here, on the bottom right, that actually takes your ONNX file, which is this binary well-defined file where you would get the weights very easy, and you can really compile it down to machine code. So if you want to obfuscate it further, of course, that's still not encrypted, you could go that way and then really ship a binary that can be executed directly.
Thank you very much. Somebody asks for a couple more examples of models that can't be converted to directed acyclical graphs. Wow, that's a mouthful.
I mean, for example, this is more like pre-processing rather than actually having an estimator. But imagine you have a pre-processing step where you do a lookup against a database. This is something where you have I/O, and this is something you would need to put basically all the data in your database as an instantiator inside of your ONNX graph. That's the only way, and then it's baked into the graph, right? Like there's no outside communication happening. I think that is another good example outside of this all recursion thing that we've mentioned. Or maybe if you have really funky Python code and you do something like while something, do this and this and this and this, it might be possible to sort of unroll this while loop and put it into something that is more static as a graph, but maybe not always.
As a caveat, technically you could extend the existing ONNX specification, like not the specification itself, but you could create your own nodes. That is like, then you are very deep on the advanced side, but nothing would stop you, for example, to create your own node that does do this particular logic, and then you would need to link it essentially to the ONNX runtime. But that would certainly be a lot of work.
He really wants to write a Lua node.
I really want to do that actually, but yeah, but technically you could write your own node that really does completely arbitrary stuff, but that would be outside of the standardized part. You would lose a lot of like sort of the reusability in this regard, but technically possible.
Okay, then one last question. We have about a minute left. Do I get a useful error when I put an sklearn pipeline into ONNX which is not supported?
Well,
so usability.
So we love sklearn to ONNX. It does so many great things, but meaningful error messages is not one of them. So sometimes you get really cryptic stuff, and we had to fix quite a lot of things upstream, especially for error messages, where we're like, again, it's a kind of tooling where if you like see a lot of red and you're like, well, it doesn't work, then maybe you need to wait a couple more years. Or how do you see that, Christian?
Yeah, similar. A couple of years, yeah, maybe you're right. But I want to be more optimistic, actually. I mean, it's a young ecosystem, but there's actually quite a lot of movement in it. There is quite some corporate backing. So I hope that it really is going to improve on a shorter timescale than 2 years. Yeah. But currently, again, there are rough edges. So if a cryptic error message is, well, they can be pretty scary, I have to admit. Yeah, but yeah, true.
Then I would really like to thank you for a very, very interesting talk. And yeah.
Thank you.